Thank you, and thank you for the invitation. Yeah, like you said, I'm going to talk about the influence or the plausible influence of Barents and Kara sea ice loss in driving future polar vortex changes. And I will, in the talk, I will stress in several parts why I think this remains a plausible hypothesis, but why it's also a difficult topic in terms of to make very strong statements about this. But okay. So let's start. Hope this works now. Okay. Yeah, just to give a very brief overview. So the polar vortex or the stratospheric polar vortex, this is one of these schematics, which you can find on the internet. So I'm talking about this stratospheric polar vortex. So it's a vortex in the stratosphere, which forms in boreal winter. And so basically it's often differentiated between two main phases. So the polar vortex can be stable or it can be very strong. So we have a very strong westerly flow in the Arctic stratosphere. Or it can be wavy, or it can be a very weak polar vortex. In the most extreme cases, the winds can even reverse, something known as sudden stratospheric warmings. And here, again, of course, stratospheric dynamics and chemistry are also relevant for ozone and other aspects of the climate system. But I'm here more interested in the downward influence of the polar vortex. And yeah, roughly one can say that if the polar vortex is stable or is very strong in winter, kind of the schematic on the left, then usually we also have a stronger, more zonal jet stream and weather patterns associated with the zonal flow. Whereas when the polar vortex is very weak, we see more of this weak jet stream phases, or especially it projects onto the negative phase of the North Atlantic oscillation. So there is there's a well-documented downward coupling of the polar vortex to tropospheric weather. And that's one of the reasons why we care about this polar vortex. So, and more precisely, the motivation I'm looking on, I'm here approaching is, again, having the schematic on the left. So the polar vortex is this band of westerly winds. And it turns out that CMIP5 models, they don't even agree on the sign of change of the stratospheric polar vortex, which I will here call SPV, under the RCP 8.5 scenario. And this is also an issue in CMIP6. So roughly half of the models project a strengthening of the polar vortex with global mean warming, whereas the other half projects a weakening of the polar vortex with global mean warming. And this is, of course, this uncertainty is, of course, an issue, again, as I said, because we know that the strength of the polar vortex is relevant for surface weather. And it was shown by previous studies that this uncertainty in the stratosphere, in future climate, that this uncertainty also counts for much of the uncertainties regarding future tropospheric circulation. So, for example, it was shown by Zappa and Shepard that, but also by Simpson et al., that kind of the amount of extreme windiness in Europe, or the pace of Mediterranean precipitation changes, that this largely depends on how the polar vortex will change. But so far, kind of the reasons for this model spread are not very well understood. So we don't really know why the models disagree so strongly on how the polar vortex will change. And in this talk, or what I'm here addressing, is what is the role of Barents and Kara sea ice loss in all this? So looking at one of these potential drivers of polar vortex changes. Okay, so why should Barents and Kara sea ice loss play a role at all? So there's, I think it goes back to the study by Kim et al. In 2014, but there are now several papers on this topic. But there is a mechanism that Barents and Kara sea ice affects the stratospheric polar vortex. And what has been hypothesized is that low Barents and Kara sea ice concentrations in autumn, which is associated with an increase in latent heat fluxes, that this can also alter the surrounding pressure anomalies. And for example, it has been linked to higher pressure anomalies over the Ural Mountain systems. And this high pressure system over the Ural Mountains, then via constructive interference, is known to lead to enhanced vertical wave propagation into the stratosphere, which we know then leads to a weakening of the polar vortex. So a warming of the stratosphere, weakening of the vortex, and then as shown before, this weak polar vortex is often associated with this more cold winter weather in Europe, but also more precipitation in Southern Europe, for example. So there is this mechanism linking changes in the Arctic, which we know are happening, to changes in the stratosphere. Via this so-called stratospheric pathway. But this is really, and this is important to stress, that this is really a very polarized, a very ongoing debate, and this is kind of a polarized discussion in the literature. And this is just showing a few of several recent papers in different nature journals on this topic. So you can maybe already see from the titles that often it's claimed that there is really a consistency or a inconsistency or discrepancy between, on the one hand, models and observations, but also between models. So we don't really have model agreement if Barents and Kara sea ice loss indeed leads to a weakening of the polar vortex or not. One should also say it's maybe regarding the influence of Arctic on mid-latitude weather and climate, which is again a polarized topic on its own. The stratospheric pathway is maybe one of the topics which is the least controversial, but still the full debate is ongoing. And the reason is really just that there's really that we have often inconsistent results between models and observations, or also between different model studies. So in this talk, I mostly refer to a paper which appeared a bit longer than a year ago, and within climate dynamics, with the title "The Role of Barents and Kara sea ice loss in Projected Polar Vortex Changes," together with Giuseppe Zappa and Ted Shepard, where we addressed this problem and where we try to kind of take a different approach, which I will try to explain. And maybe just to give a little teaser, so maybe what we try to do a bit differently is, on the one hand, that we try to come up with a better estimate of the causal effect of Barents and Kara sea ice loss on the polar vortex using a so-called causal network approach. So that's one part of this paper and of this talk. And the other aspect is that, in contrast to these other studies, we really take a deductive approach or deductive analysis in the absence of a statistically significant signal. But again, I will come. I hope this gives you some interest in this talk. But I will again discuss both aspects in the next 30 minutes or so. Okay, so to give some further background on what motivated our study, was a paper by Manzini et al. In 2018 called "The Nonlinear Response of the Stratosphere and the North Atlantic European Climate to Global Warming," which appeared in GIL. And in this study, they used a single model, a large ensemble. So they used the Max Planck model. They had back then 68 ensemble members, but now they actually have 100 ensemble members, where the results are consistent. And they took the 1% CO2 experiment, so very strong forcing. And what they found, so this plot shows the latitude height section, and kind of what so the polar vortex region is really this Arctic above here in the stratosphere. So what they showed was that for the first 2K warming, this period here, they found a weakening of the stratospheric wind, so a weakening of the vortex. But then for the next 2K warming, they actually found a strengthening of the vortex again. So again, the polar vortex weakens during the first 2K warming, but then it recovered during the second K warming. So there was some kind of nonlinear behavior to global warming. And what they hypothesized in this paper, so they didn't look at this in detail, but kind of when they looked for differences between these two periods, they found that in this first 2K warming, there was a decrease in Barents and Kara sea ice, whereas in this for the second period, all the sea ice was already gone. So kind of this forcing, there was no increase in this potential forcing from sea ice. So they hypothesized if this is related to sea ice loss, given again these previous publications which claimed an influence of sea ice loss on polar vortex changes. And this is from basically the same data, where you just see the polar vortex change as a time series now. So you first see this weakening of the polar vortex with time, and which then recovers and actually at some point even becomes or strengthens again. So kind of the first question we addressed in our paper was also to ask if there's also evidence for such a nonlinear polar vortex response related to sea ice loss in the CMAP5 ensemble. So where we have more climate models, well, less ensemble members usually, but different climate models. And we can also find evidence for such a nonlinearity. So we in the study we considered 35 different CMAP5 models. We took the RCP 8.5 runs from 2006 to 2099. So we concatenated, well, also used the historical runs plus the RCP 8.5 runs for the 21st century. And during this talk, when I compute some changes, I compute them relative to the mean from 1960 to 1990. So this is kind of my reference period. The reason that in this period, Arctic amplification and sea ice loss is not as pronounced as it was after the 90s. So, and this plot now shows the change of the polar vortex in winter, in this case, January, February, March. But I don't show the change as a function of time, but I show the change as a function of global mean warming levels. So the x-axis shows the different warming levels, the y-axis shows the polar vortex change, and the different gray lines are the different climate models. And the blue lines show the ensemble mean. And the reason there are different lines is just because different models reach different warming levels. So the dark blue line is, the darkest blue line is the mean over all the models which reach 5K warming. The next one is the mean over all the models which reach at least 4.5K warming, so including these as well, etc. And what you can first of all see is that really the spread between different climate models. So some show a weakening of the polar vortex, others show a strengthening of the vortex. This is kind of this inconsistency, the spread in the ensemble. But if you look at the ensemble mean, we see, well, a slight indication for this nonlinearity, let's say if you want to see it. So you see in the ensemble mean, there's first a weakening of the vortex up to roughly 2.5K warming. And afterwards, there's no further weakening, or even for the very warm moments, even some strengthening. Where consistently, or not consistently, this shows the change of Barents and Kara sea ice now in autumn. Again, also plotted for as a function of global mean warming. And you see there's also not some non-linearity in the way sea ice changes. And the reason is just that at this point, it already samples more and more models which have already become ice-free. So the change is not ongoing, but it just this kind of the ensemble mean flattens out. But actually, there's really a huge difference across models regarding the year they become ice-free. So here on the x-axis, you see the year and for the different climate models when the Barents and Kara seas in autumn are ice-free. And you see already this ranges from 2050 to well, more than 100 years later. So it really depends, or the models really disagree when they become ice-free, but we can actually basically understand or predict the timing well just from using the climatology, so kind of the amount of sea ice they have in this reference period divided by the global mean warming level. So models which have little sea ice and warm fast will be ice-free early, whereas models which have a lot of sea ice and only warm slowly, they will be ice-free late. Yeah, this makes total sense. So what we did then was to kind of, we split the ensemble in two parts, and those models which are ice-free early, so before the end of the 21st century, so the blue models here, and those which are ice-free late, and computed the ensemble mean again, so for these separate models. So again, this is separating between late and early ice-free models, and you see the late ice-free models, so they keep losing sea ice, so we have this linear decrease in sea ice with global mean warming as expected, whereas the early ice-free models, we see now this non-linearity even stronger, and just because by choice, this ensemble subset samples more and more models which have become ice-free. So there's no further sea ice loss. And we do the same for the polar vortex change, we can also see now a even more pronounced difference. So the models which keep losing sea ice, they show this in the ensemble mean at least, this almost linear behavior with a weakening of the vortex, whereas those which have become ice free at some points, with the blue lines, they show some weakening first, but then they strengthen. And again, we can also just show this as a boxed viscous plot. So this is the change of the polar vortex before they become ice free. So accounted kind of for this timing, this different timing they become ice free. And we see that most of the models, or 75%, show a weakening of the polar vortex, whereas afterwards, so when they have become ice free, those models which have become ice free, they show a strengthening of the vortex afterwards. And importantly, this difference is positive. So there's more strengthening or less weakening after having become ice free. So well, to summarize this first part, so we found for CMIP5 that the vortex weakens as long as Barents and Kara's sea ice decreases, but it's strengthened again once the Barents and Kara seas are ice free. And so this is consistent or qualitatively consistent with the results from Manzini et al. So the second question we then address is that can we, so we find this nonlinearity seems to be related to sea ice loss, but of course this does not prove that there is any causal influence of sea ice loss on the polar vortex. So the second question we address then, if we can find in the CMIP5 ensemble evidence for a causal influence of sea ice on the polar vortex. I'm kind of advocating for some use of so-called causal networks. So again, I'm interested in how strong is the effect of sea ice on the polar vortex, SPV. So this is kind of the effect I'm interested in. And again, I mentioned in the beginning that this is a polarized debate. The reason is that really different mechanisms or potential confounding mechanisms, which make it so hard to quantify this effect just from data alone. Plus, given this issue that models often disagree on this kind of effect. So what this so-called causal network on the right, what we did here was we tried to summarize the literature on this topic and kind of try to put together the different competing and confounding mechanisms which might bias our estimate of the effect of sea ice on the polar vortex. And well, first of all, you see this mechanism, what I proposed, what I showed in the beginning. So from Barents Kara sea ice, there's an influence of Ural sea level pressure, which leads to an increase in V prime T prime, so increase in vertical wave activity, which then leads to a weakening of the vortex. But then again, there's also Barents Kara sea ice is strongly autocorrelated. Also importantly, Ural sea level pressure also is known to affect sea ice loss. North Pacific sea level pressure might be a confounding factor, which if influences both the polar vortex strength, but also could influence Ural sea level pressure or Barents Kara sea ice by a Rossby wave propagation. And there might even be also other drivers from the tropics, which play a role. So this is to say it's complicated. And explaining why it might be so hard to kind of quantify this effect from sea ice to the polar vortex. Again, we use this causal network approach. The idea is that if we first summarize all these hypothesized mechanisms first, it's way easier to understand, or this kind of guides our statistic analysis. So how to now isolate the effect of interest. And in this case, I'm not going into too much detail. It's important that if we block or if we regress out the influence of the North Pacific sea level pressure, so this kind of common driver, we already accounted also for the influence of the tropics, because they would be mediated by a North Pacific sea level pressure. That's at least what we assume. Furthermore, we have also to account, or this is the main issue of this Ural sea level pressure, which is both potentially a common driver, but also kind of a mediating factor. And we play around within different time lags to account for this issue. So in summary, what we get is that we express the polar vortex in winter as a function of Barents and Kara sea ice in autumn. And we also control for these confounders, so North Pacific sea level pressure, Ural sea level pressure, again, these confounding factors, in the hope that kind of this estimate here gives us the causal effect. So what kind of the point I would like to make here is that in general, causal networks make these different assumptions of these different mechanisms really explicit and help us really to identify where information is propagating or is flowing, such that we can come up with a kind of optimal estimate to quantify the cause effect of interest. And for the sake, well, I don't unfortunately have time to go into more details here, but I would like to promote this other paper which appeared recently, where we explained this kind of causal inference theory or framework, and how this is useful to really quantify causal path weather of teleconnections. And in this paper, we also addressed this problem with accounting for quantifying the effect of sea ice loss on the vortex, but there are also other examples of different teleconnection, and there's also Jupyter notebooks which come with the paper so that you can follow the different examples hopefully more easily. Okay, so but back to our problem. So we're interested in quantifying the causal effect of sea ice on the polar vortex, and we try to quantify it just using Barents and Kara sea ice in autumn plus these different confounders. And so this regression coefficient A is what we interpret as the causal effect, or which is our estimate of the causal effect or causal influence of sea ice on the polar vortex. And then we estimate this regression coefficient, so we computed for all the different climate models over the historical runs. And we also do this for different moving windows of 39 years, which kind of coincides with the observation record we have. And this plot here shows for the different models, shows the spread of this regression coefficient A, so this assumed or this causal effect. So what you can here see already, there's really a large spread of this regression coefficient. We show the standardized regression coefficient because the models also have very different variability in the stratosphere and sea ice. And you can see really there's large spread. So for example, just taking 2 examples here, one shows consistently a positive regression coefficient, what we would expect actually. So less sea ice leading to a weakening of the vortex, with other models show consistently a negative regression coefficient. This shows here the distribution over all the regression coefficients, and the cross here shows the same, so that shows this regression coefficient A, or this causal effect for the observation. So in the observations, the effect seems to be stronger, but it's still within the spread. So it could be just that there are 2 possibilities here. So either the effect would be what we find in the observations can just be high just by chance, and it's actually much smaller. The second potential explanation is that the models underestimate the effect of sea ice loss. In this paper, let's say we didn't care for this aspect, so this is this has been discussed in several different publications. So, and our results, let's say, are consistent with this conclusion that we cannot really say whether it's the models underestimating the effect or whether it's the observation record being an overestimate of the true effect. This shows the means, the box and whisker plots for the means over the models, and you can hopefully see that this is slightly positive. So the mean causal effect we find for the different models is really as small as 0.05. So most of the models show a positive effect, as we would expect, but it's really tiny. So it really ranges, or the 75% of the models show some effect between 0.025 and 0.1. So it's really small. And this brings us to kind of a typical dilemma, where, especially for this debate of the influence of Arctic sea ice loss, but also maybe a general one in climate science. So again, we estimated the effect of the polar vortex, with A being the influence of sea ice loss. And so our typical null hypothesis would be there is no influence of sea ice loss, so this regression coefficient is 0. And the alternative hypothesis testing in this very conventional null hypothesis testing setup would be there is an influence, so A is not equal to 0. So now we find A is roughly 0.05. So what do we do with this? Based on significance testing, we cannot reject our null hypothesis. So we cannot say, we cannot make this, okay, it's significantly different from 0. That's why we reject the null hypothesis and take the H1. But of course, not rejecting the null hypothesis doesn't prove the null hypothesis. So yeah, so we left this with this dilemma that we that we cannot make a statement if there is an effect or not. And importantly, also this null hypothesis, it cannot really explain this detective nonlinearity. That's why, let's say, we have reason to go to do further analysis. So what we did instead was taking this deductive approach. So we don't care if there is an effect or not, but we assume there is a causal effect of sea ice on the polar vortex. And we are just interested in the implications, but again, under the assumption that there is an effect, which we didn't prove. And again, we also don't know exactly how strong the effect is, but a plausible range, if you think of this fox and whisker plots, before, a plausible range is really as small as 0.025 and 0.1. So yeah, if there's one, it seems to be small. At least this is what proposed by the CF5 models. And again, it seems to be, this deductive approach seems to be justified just because there is this nonlinearity, which seems to be related to CS loss. And the other aspect, which I think we should yeah, maybe even stress more, is that we know that sea ice will decrease in the future. So if there's an effect, even if we are not certain about it, we should care about it, and we should care about the potential implications, just because we know there is this decrease in sea ice loss. So we should understand potential risk associated with this. So I kind of come to the last part of this talk. So the third question is, what would a weak causal effect of sea ice imply for future polar vortex changes? Again, not saying that there is an effect, but just what would it imply? And related to this, or kind of to justify this deductive approach, we of course have to keep in mind if there are any implications which contradict our assumption of an effect. So what we did here is we kind of decomposed the polar vortex response. So this is, again, this is the projected change I showed in the beginning. So just now the ensemble-mean is just, yeah, it's shown in the gray colors, but this is basically the spread I showed before for the different CMIP5 models. So this is the projected change. Now we take an assumed causal effect, CE, or this is the relation coefficient A. And now I just assume it's 0.05. Again, this within this plausible range, and ask, okay, what would be the contribution of sea ice loss? So I can just compute the projected sea ice loss multiplied by this causal effect, which I assume to be true. And so if and this would then be the change of the polar vortex from sea ice, due to sea ice. So if we had a world where there was only sea ice loss, we would conclude that the polar vortex would weaken, and roughly, and you can already see it's in similar magnitude. And then the remaining effects are the residuals. It's just this panel minus this panel. This would be the effect on the polar vortex in a world, in a warming world without any sea ice loss. And you can see now that actually in the ensemble mean, we now see a consistent, or we see a strengthening of the vortex with global mean warming. So we did some more analysis, but maybe what we can what we roughly show in this paper is that a weak causal effect of sea ice loss, so really assuming something as tiny as standardized effect of 0.05, that such a weak causal effect can actually can explain, not can affect, but can explain the different signed polar vortex response to global mean warming. It actually can explain also all of the ensemble mean change and most of the projected change. But again, this is conditional on the assumption that there is an effect. Yeah, so but this is kind of the deductive exercise we can do. Again, I mentioned we have to always ask whether this in a way contradicts our assumptions from the beginning. So the one question, or what was also asked by the reviewer, is that if these kind of lines here, if these are really more linear than these ones, and this is of course a very justified question. So what we also did is we tried to kind of, again, to justify this deductive approach. We asked if there's this evidence against our assumptions. So we do this with so-called base factor analysis, which is actually very, very intuitive. So again, we the two hypotheses we address is, on the one hand, there is no influence of sea ice loss. So the change of the polar vortex would be expressed as a linear function of global mean warming, has some noise. And the alternative hypothesis, or kind of if there was an inference of sea ice loss, would be that the residuals, so if I remove this nonlinearity due to sea ice loss, that this would scale more or less linearly with global mean warming. And again, I'm not sure how strong exactly this effect of sea ice is, but I assume kind of a plausible range between also A to B within 0.025 and 0.1 within this interval. And this is just one example for one model, how this looks like. So this is the raw data. And basically the idea is you can fit a linear line, regression slope, and you see the residuals. So is this data more linear than this one? And in this case, you already see that it looks, the residuals have a better linear fit than the raw data. But of course, we want to quantify this. So we compute the so-called base factor. This is just the probability of seeing the data under the null hypothesis divided by the probability of seeing the data under the alternative hypothesis. So, and given that we assume them to be Gaussian, it's actually very easy to compute these probabilities. For the base factor, there is kind of, so if it's around 1, so if the probabilities are the same, of course, then there's no evidence. And only if the probability is really high, let's say higher than 10, so that this is 10 times more likely to see the data under the null hypothesis, we would conclude this as evidence for the null hypothesis or evidence against the alternative hypothesis. What we find here for the CMAP5 data, this is showing all the different models, and well, here in small is always plotted the base factor, so yeah, you're not expected to see anything here, but we actually find that in most of the cases, the base factor is close to unity, so it's close to 1, meaning that the data is equally likely under both hypotheses. So it's, again, this is no proof of sea ice having a causal effect, but it's, again, also no proof against it. So there's no contradiction to our assumption of a weak causal effect. And importantly, this also means in a hypothesis testing setup that we are allowed to retain our hypothesis. Okay, so I have a final slide of another thing we do in the paper is that, again, just within this deductive approach, we can also make then things like a bias adjusting for an unrealistic amount of sea ice. So this shows the box and whisker plots of this sea ice climatology for the different CMAP5 models, and the cross here is the climate the observational value. So you see most of the models actually have too much sea ice, and well, and also several models have too little sea ice. Again, if we assume there is a causal effect of sea ice on the polar vortex, this would also mean that those models which lose too much sea ice, so unrealistically amount of sea ice, that the response of the polar vortex would be overestimated, whereas those models which have too little sea ice, the response would be underestimated. I'm giving 2 examples here. So for example, if you focus on the red line first, so this is MyRock ESM, the light red line shows the projected change. You actually see that the strong strengthening just appears at some point or starts here. And this is when the model has become ice-free. But this model also has too much sea ice. So we can, so this, the strength, I say the correct way now. So we have to bias correct. No, sorry, it has too much here. So we have to bias correct for this too strong response. And again, taking different amounts of causal effects, that would be the adjusted projected polar vortex change. No, sorry, I said it wrong. This has too little here. So this model here shows actually strong weakening. CMCC, CCM, but this also model, this has too much sea ice, and this means that at this point it exceeds the physical possible amount of sea ice loss compared to the observations. So again, we bias correct for this too strong weakening due to sea ice loss, and this would be the bias corrected estimate of projected of polar vortex changes for these different plausible causal effects. So in these cases, you see that that bias or this unrealistic or sea ice actually has a huge impact. And this can be, so for individual models, this can have a huge effect, but for the ensemble mean spread, we didn't find any large implication of this effect. Okay, so I come to the conclusions of the summary. So again, we found in this paper evidence for a nonlinear polar vortex response to global warming in the CMM5 ensemble, dependent on the time or coinciding with the time the Barents and Kara seas become ice-free. And this is consistent with the previous single model large ensemble study by Manzini et al. We then tried to see if we can prove a causal effect of sea ice loss using causal network and causal network framework, but it's really difficult to isolate this effect from data. But what we found is that it's plausibly, or at least in the CMM5 model, the effect is plausibly only very small. So we then followed this deductive approach to work out these implications of an assumed causal effect, again, just because we know that sea ice loss will decrease, so we have to understand related risks. And we found that even this tiny effect can actually explain large parts of the ensemble mean and spread, as well as the different signs polar vortex response to global warming. So, and the reason again is just because the amount of sea ice loss is so massive that a tiny effect would already have huge implications. Importantly, we didn't find any contradictions to our assumptions, which does not prove the assumption, but it also means it remains a plausible explanation for future polar vortex changes. And I didn't have time to show results here, but I can mention that currently working on updated results in CMM6 and also using some different single model large ensemble ensembles, where again the story seems to be similar, that we can't really prove it, but it remains a consistent hypothesis, and we see the similar non-linearity, which potentially is related to sea ice loss. Yeah, I think I talked a lot, and yeah, just say thank you for the attention.